welcome to the NIU AINO seminar. I'm Maliha. I'm a PhD student from the Computer Science department. So this presentation is about direct preference optimization, also known as DPO. So the core phrase is your language model is secretly a reward model. So this process improves the language model using the human preferences. This process doesn't work like the standard reinforcement learning from human feedback. It doesn't use an explicit reward model or any reinforcement learning. So how this process works, we will see in a moment. So this is the pipeline for the presentation, and also this paper is introduced by the researchers from the Stanford University. So first we will see what is preference, the basic question. Then we will go through the RLHF pipeline, the phrases, and then we will introduce the DPO pipeline. And for these two pipelines, we will see some equations and try to understand it as much as we can. And then there are many experiments in this paper, but I have mentioned 3 core experiments from this paper. Then we will see some limitations mentioned by the authors. So let's start with the basic question. What is preference?
Excuse me. So this is the original paper for DPO?
Yeah.
Okay. Which year it was published?
2024.
Okay.
So we all use language model in our daily life, and if you have already used ChatGPT, which I assume that you did, you see this scenario that when I ask ChatGPT a question, sometimes it gives us a pair of responses, two responses. You can choose which one you prefer. So its preference data is human comparing 2 responses and choosing one. So it can be like, suppose the prompt is write a Python function to sort a list of numbers. You can see there are 2 responses. One is preferred, denoted as YW, and one is rejected, denoted as YL. Human beings usually prefers small and concise answers. If it's long and confusing, we usually reject those answers. Then again, if it's a factual prompt, is the earth flat? The preferred answer would be no, the earth is not flat. It's kind of spheroid. But what if the LLM gives you like, some people prefer it flat, some people doesn't prefer it flat. We don't want these confusing answers. So this is what a preference means in terms of language models. Now, this paper uses a preference dataset. So this dataset, how does it look like? It has 3 things. The X is the prompt you are asking, and there are 2 responses per prompt. One is YW, the preferred answer. Another one is the YL, the rejected answer. So let's start with the RLHF pipeline. So it's called reinforcement learning from human feedback. Suppose you are trying to teach your cat a trick. If it can stand up, you are going to give the cat a treat. So this process reinforces in the cat's mind that if it can do it correctly, it will get a treat. We treat LLM kind of like that. We try to bribe it with rewards. So how does it work? The phase 1, the supervised fine-tuning. So the input is that you have a pretend LLM. You fine-tune that LLM using labeled dataset. It can be a big corpus from maybe Wikipedia. And after you fine-tune it, you will get something like PySFT. So the first phase output, so the first phase output is a base model. It's your reference model. In the upcoming phases, you will see that we'll denote this base model as our reference model. So what's the goal? Why do you need to fine-tune a pretend LLM? You want to make sure that your LLM still able to do the generic tasks, for example, summarization, text generation, or communication. So this is the phase 1, and the objective is pretty simple because it's a basic language model. The objective is something like this. So this is kind of the objective for the language model. O is the token, X is the prompt, T is the token at timestamp, and less than T is previous token. So how does language model work? You give the prompt, you give a previous token, and it's an autoregressive process, and the language model predict the next token. So you want to maximize the likelihood that the language model predict the correct token. So this is the first phase objective. Then you go to the second phase, that's the reward model. So now in second phase, you have the input, you have the base model, which is your reference, and you have preference pairs. So the preference pair is the prompt, the YW and YL. These preference pairs coming from the dataset. How did we build up the dataset? We will see in the next equation. For now, just imagine that you have the input, the reference model, and the dataset. So the process is that you now want to train a reward model using this input. And the goal would be that your reward model should be able to give reward score to your each responses. It can be the preferred response, it can be the rejected response. So the goal would be scalar reward scores. So now when you have trained the reward model, you go to phase 3, which is fine-tuning the reinforcement learning. For this process, as an input, you have the reference model, you have all the reward score for your responses. Maybe it's a preferred response, maybe it's a rejected response, and you have the prompt. Now, in this phase, you want to maximize your reward. So as much as you can maximize your reward, you can drive your LLM to always generate the responses that human would prefer. So the output of the phase 3 would be a aligned language model. Why is it called aligned? Because after phase 3, at least we are claiming that the reward model would think like the human. That maybe the human would choose this answer, maybe he would reject this answer. So the output will be an optimized language model which is aligned with the human preferences. So this is how the figure look like. If you can see, we have the preference data, 2 responses, you train the reward model, and you use the reward scores to train the LLM policy. So when I say policy, it's actually language model. So policies means given a prompt, how well your language model is responding. So you train the optimized LM language model, then there is a loop. So it's kind of a feedback loop process. So every time you train the LLM, you give a feedback or you can, collect some samples, you retrain the reward model, then you again collect some reward score, and it's a loop. So how does this all make sense in equation wise? So let's start with building the data set. So if we have already read like many research papers, we know that we create data set by sampling from a distribution. So this is the distribution for the DPO work. So there are some framework for the distribution equation. The DPO paper uses the Bradley-Traylor preference model. So the Y1 is the preferred answer, the Y2 is the rejected answer. So this probability means the probability of Y1 is preferred over Y2 given a prompt X. For example, here is a description how the dataset can look like, that the prompt may be where is Shanghai. The preferred or good answer would be Shanghai is a city in China, and the rejected answer would be like, the city maybe not exist. Or maybe it's a fact, what is 2 plus 2? The answer would be 4, but the LLM is saying, it's a very difficult math. That's a rejected answer. So when you have the probability distribution for all the Y1 preferred over Y2, you sample from this distribution and create a data set D. So that data set has, if you can recall, the prompt, the preferred response, and the rejected response. Now, when you have the data set, and as I said, the phase 1 is all just fine-tuning a reference model, you try to train the reward model. So if you want to train a model, you need a loss function. How does that loss function for the reward model look like? This is how. If you can see, we have a sigma function, and it's like a cross entropy loss. We have a log, and this is the difference between the reward score of the preferred answer and the rejected answer. So we want to minimize the loss, but we want to maximize the gap between the reward score. There are two objectives. Now the question is, we had this equation, probability distribution. How did we go from this equation to this one? It's a very simple analogy. So they are claiming, if you can you see my cursor? Yeah, you can. If you can consider this part, the numerator part, as a term A, and this part from the denominator as a term B, you can write this probability distribution as this form, epsilon A divided by epsilon A plus epsilon B. And they are claiming that this equation can be equivalent to sigma A minus B. How? Simple math. We divide both the numerator and denominator, or epsilon A. These two portion cancels out. If you take common epsilon A, the denominator becomes like this. And if we know how epsilon works, we can write this portion as B minus A, epsilon B minus A. And if you take minus common, it becomes like this. Now if you can see, this equation kind of look like the sigmoid equation. So you can convert this as, so this is like this, sigma x, so you can write this equation as A minus B. Did I make it clear, understandable? Okay. So now you have turned this equation is sigma A minus B, put back the original terms in place of A and B. So if you put back the original terms, it becomes like this. That's how you got the loss function. So now you have a loss function, you have trained your reward model, your output is reward score for each responses. Now you go to phase 3, which is optimizing your language model. So now you need an objective. So the objective is this one. This is the RL fine-tuning objective. I will try to explain what this means. So the X is the prompt coming from the data set, the Y is the response given the prompt X, and this is the reward score for each response given the prompt X. Your objective is to maximize the reward. This is your objective in the third phase. Now what does this whole term doing? This is a KL divergence. You can assume KL divergence as a distance, but I want to be clear, it's not distance, but it's more interpretable if you consider in this case as a distance. So what KL divergence is doing, you do want your optimized model to maximize the reward and work more efficiently, but you don't want your language model to drift far apart from your reference model that you trained in the first phase. So this one is the reference model, this one is the model you are trying to optimize. So KL divergence is just making sure that your optimized model is more efficient but can still do the generic task like a simple language model. So this is the whole scenario. You finish all the 3 phases, you have the reinforcement learning human feedback. Is there any question till this?
Can I understand that the basic idea is, instead of fine-tuning the model with the YW and the YL pairs, you want to find a function that can give you a score without using the YW and the YL pairs. And how the function looks like? Is that a model, or is that just a function?
So the reward model is, yeah, it's a model.
It's a neural network model?
Yeah, it's a neural model. So it's the output is the scalar score for each response.
What's the architecture of the model? Is it MLP or which architecture?
I don't kind of recall what's the architecture of that model.
Is it reward model?
It's a reward model, so it's a neural network. It's
the transformer type problem.
Oh, it's a transformer.
Yeah, it's like so the fast layer will be changed. So actually in the PPO, they was they train reward model and critic model at the same time, and then change the fast layer.
Okay.
And
Is it large? How large is it?
So like For me, I trained with like just 2.5 billion coding model.
Uh-huh.
For the reward model.
Yeah,
For this
the
paper,
reward-
I think it's 6 billion.
Yeah, for
Yeah, for
they
this
use
paper.
the I
Yeah.
think GPT and something.
Yeah, GPT.
Thank you.
How big is the reward model compared to the model? Are they about the same size, or it's?
It depends on tasks actually. Like what type of tasks you're working.
Yeah, because it is one of their limitations that they said that we have only explored 6 billion parameters model, but you can explore more. It is mentioned in the paper. So, I want to clear that each process for improving your language model works fine. So RLHF process works well, but we as researchers, we have a habit to make it more efficient. So we try to find some limitations. The limitations of this pipeline is that you have to train 3 separate models, like the SFT or the reward model and the language model you're trying to optimize. So it's kind of computationally expensive. And then there is a feedback loop. Every time you're training, you're collecting samples and retraining the reward model. So this feedback loop can slow down your whole process. And the and the RLHF process use the PPO algorithm, which is kind of sensitive to hyperparameters. And if you know how PPO works, it needs a reward model, it needs the value function, it needs the advantage. So there are a lot of calculations.
When will you retrain the reward model?
So
After you train the LLM?
yeah, it's like a constant converge process to try to make it converge. So the loop is that.
The reward model does not depend on the model part. LLM depends on the reward model to train.
Yeah, but every time you optimize the language model policy, you collect the samples and see if the reward model can generate higher score for the answer that you just chosen in the LM policy.
Okay. When your model changes, the data
Yeah.
changes.
It's like until you converge.
Okay.
And there is another problem is reward hacking. So what if your cat learns to trick you? It doesn't actually stand, but it makes you think that it's standing and grab more treat. So it's kind of a problem of reward over optimization. The language model game your own game with the reward score and doesn't actually improve. So eliminating this drawback, we introduce the GPO. So in the left, we have the RLHF approach. If you can see, there are 6 steps that I just described. But the GPO approach is just 2 steps process. You collect the preference data, you run the GPO loss on the optimized model you are trying to optimize and the reference model, and boom, you have a efficiency in improving your language model. So no external reward model, no complex reinforcement learning. So the picture is kind of simple. You have the preference data, you try some calculations, and you have the final LLM. So what is this try some calculations? So what they did, they took this equation from the RLHF and they took this objective and find the close form of this objective. So the first equation of the GPO is actually the close form of the objective function from the RLHF. If you can see the equation, it has a new term called the ZX. It's a normalizer function. We are dividing it. So, and still the function has an explicit reward score here. So the derivation from the close form to this, from the objective to this close form is kind of complex. I kind of didn't put it in the slide, but it's in the appendix of the paper. So if you want to work directly with this close form, you have to calculate ZX, the normalizer function. And if you can see, ZX is calculated over all the responses you generate, and it's very, very computationally heavy function. So yeah, you did get another function, but you kind of put yourself in danger by choosing a computationally heavy function. So now your goal is you need to eliminate this function, so you don't need to calculate it. How do you do that? They reformulate the closed form equation to this equation. This is the reward score equation. Now the question is, how did they go from the closed form to this reformulated equation? the analogy is again kind of simple. You take log on both sides of the closed form equation, and if we know how logarithm works, if it's a multiplication, it's a positive. If you are dividing it, it kind of subtraction. Then this one is again multiplication, so this one is again plus. This log and exponential kind of eliminate each other, and the whole function becomes like this. Now, we have seen this reformulation in our childhood, right? If you have this, you can write it like this, right? You just put everything on the other side of the equation equal. So that's what they did. They keep the reward score function and they put everything the other side of the equal, and that's how the closed form equation become the equation this one. So now you have a reward score function. If you can remember the Bradley-Terry model, you said that the equation can be written like this, sigma a minus b. This one was the reward score for the preferred answer. This one was the reward score for the rejected answer. So now you take this reward score equation and put it here in place of a, in place of b, in terms of yw and in terms of yl. When you put those equations, you can see these two terms cancelling each other out. So now you have an equation. First, you don't have an explicit reward score in your equation. Second, you don't have a computationally heavy zx function anymore. So now your loss looks like this. As you can see, no zx and no explicit reward score. I want to clarify one thing. GPO eliminates the concept of training separate reward model. It doesn't eliminate the concept of reward, because it's saying your language model is secretly a reward model. You don't need another reward model. How? Because this ratio is actually a reward score. So you are not eliminating the concept of reward, you are just eliminating the concept of training explicitly another reward model. So the log ratio is just how much more likely the fine-tuned model, the model you are trying to optimize, the pi theta, prefers YW versus your reference model. And you want to maximize this gap as much as you can. So if you want to minimize the loss, you can take a gradient. So if you take the gradient of the DPO loss, it becomes like this. It has three terms. Let me explain. This one is the likelihood of choosing the preferred answer. This one is the likelihood of choosing the rejected answer. So we try to increase this likelihood. So we try to push the policy model to assign higher probability on the preferred responses, and we try to decrease this likelihood. So we are trying to push the policy or the language model to give lower probability to the rejected answer. Now what the first term is doing? It's actually a weight. If you can see the function, the first term is the reward score for the rejected answer. Suppose your model makes a mistake. It gives a higher reward to a rejected answer. So if you have higher score for this portion, this is a positive answer, right? If you subtract it. So if this is a positive answer, you are putting more weight on your loss, and you are saying, you're telling your model, hey, you made a mistake. So it's like focusing the training on the hard examples when the rewards are mismatched. So that's how the whole DPO process works. You don't have explicit reward model, you don't have reinforcement, you don't have a loop, you just have a simple DPO loss, but it works much better than the previous models. So I will go to the experiments. So do you have any question until then?
I have a question. So if like for DPO, if a model has multiple response, like at least two response, so what if there is no preferred or rejected response, both are equally? So what will be the case then?
Yeah, so as far as I understood the paper, they said something like out of distribution. What you are saying is out of distribution, because the DPO paper is like trained on a data set that is already annotated as preferred and rejected. So it's the probability that we created. But they said that they haven't explored what it will look like if you train it with unseen or out of distribution data set. For example, the prompt shifts or the task changes. So it's a 2024 paper and it's been 2 years, so unfortunately I haven't checked if they actually overcome this limitation yet. Okay. So in this paper, they tried many experiments to claim that their process works the best. So I have mentioned 3 core experiments. The first one is controlled sentiment generation. The data set is the IMDb movie reviews. We will see how those working. And the second one is the TLDR summarization. So this means too long, didn't read. So it's a Reddit TLDR data set. The third one is the single turn dialogue. So it's a human AI conversation. There are 170K data. So how all these experiments working? The first one. So for this first task, their data set was IMDb movie reviews, but they didn't take the whole review. They took 2 to 8 prompts. For example, it's like, am I taking the wrong one every time?
Do you have some real data in your slides?
Yeah,
Sure.
real output.
I mean, the
So this
training-
one doesn't have one. This one.
No, I mean the training data.
No, but the example I showed here is kind of a snapshot, but it's not from the direct, like literal data set they used. But the data set looks like this.
Okay. I go back to the review data.
This is summarization. It's a second experiment.
I mean, go to the IMDb data. Yes. Yeah, experiment. How was the data collected?
So the data set is that they went through the IMDb reviews and they parsed the first 2 to 8 tokens. For example, the token may be I really thought, then blank. They didn't do the rest of the tokens. Then the movie was this token. They didn't fill up the whole review. So the task was that the model needs to be able to generate positive sentiment and finish these reviews.
And then how is that labeled?
So the label is that for every prefix they have 4 preferences. So every prefix they have 4 responses, and they are using a sentiment classifier to give a sentiment scores to each of those 4 responses, and they are taking the highest sentiment score and the lowest sentiment score.
Sentiment score.
Yeah, because they use a sentiment classifier. So they said that this task does, the rest of the 2 tasks directly aligned with their thought because it's a preference pairs only. But this one, they are not using a reward model exactly, they are using a sentiment classifier. They're giving sentiment score.
Okay, whether sentiment about whether that's response
Positive
is
response or not.
positive enough.
Yeah.
Oh, it's not about whether it looks real or not. It looks
No.
well. It's
No.
okay, and it's by a sentiment classifier. Okay.
Yeah. And the reward is the KL frontier, the KL divergence.
But then all the tool again depends on the reward model. They trying to get rid of the reward model, right? Because they don't want to train a reward model. But if they construct their data,
Yeah, I got confused here too because they explicitly mentioned that the next two experiments perfectly align with their two response preference data set, and they are not using a reward model. But this one, I don't know why they did that. It doesn't even use a
how about other data? Do they also use the reward model or using?
This is the second one. So as you can see, there is no score generating model. They have a base model, the reference model that was trained on the human summaries, and the evaluation was GPT-4 win rate.
GPT-4 win rate. What is
This
that?
means that how many times the GPT-4 is choosing your model response over the data set that is already labeled as the preferred answer.
Who labeled the preferred answer?
It's human annotator.
Human annotators.
Yeah.
How many data do they have? The annotation do they like going to hire people to look at the Reddit and the annotation, or they're just using based on a Reddit comments, something like that, or just directly
They
human
didn't mention
annotators.
the whole process. They just said that the human annotator.
Human annotator. Cool.
So, as I was saying, the dataset is the movie reviews from the IMDb, but some tokens. For example, the I really thought. The preference is that for each token there are 4 responses, and they are using a sentiment classifier to give a sentiment score, and they are choosing the best score as the preferred answer and the lowest score as the rejected answer. And the base model was GPT-2, and the evaluation was the KL divergence. So if you look at the graph, the x-axis you have the different KL values, and you have y-axis in the reward. Every dot is a trained model, and the yellow one is our TPO. And as we can see, it's getting higher scores for kind of neglected divergence. And you can see that we have a red line here. That's the previous PPO. It's kind of disappointing if you compare it with PPO.
How is that disappointing?
Because if you can see, this is expressing how your optimized model is diverging from the base model. And this curve is more like, how do I explain it? If you compare it with the DPO, it's not giving you an optimum result if you compare it with the DPO model's work.
So every point should be starting from the same place, right? The origin, or something on the left. When KR is 0 means that your policy is still the
Yeah, if KR is 0, you're ignoring
it's a
the
reference policy.
yeah.
And when your policy is
Yeah.
changing away
And the
from
more
reference model,
reference model. And maximum reward score for the DPO lies within less diversity. At least I understood it in this way.
the reward here
Yeah.
and the reward in that data collection.
It's actually I
Are
think it's
this-
like skeletons, sentiment scores. They're referring it as a reward.
So the reward model is used both in the data set construction
Yeah.
and the model evaluation.
Yeah. The model evaluation, they said that the model evaluation is actually KL frontier, not the reward score. They're trying to see that without drifting far from the reference model, if you can get maximum rewards or scores.
Oh, okay.
Yeah.
Oh, okay, so the DPO is better because when
It's
KL is
getting-
5, not
Yeah,
not far away
yeah,
from reference
yeah,
model, it's good already.
Yeah.
Okay.
Okay. The the second one is the summarization task, and the data set was collected from the Reddit. The too long didn't read, and they said that the preferences or human preferences came from a open RLHF paper. So the base model was the GPT-J, and the evaluation is here the judge is GPT-4 and the evaluation is GPT-4 win rate, which means how many times your GPT-4 chooses the response your model generated. And they tried this experiment with different temperatures, or you can say settings. So this is the GPU curve. As you can see that, this is the threshold. So if it's above 0.5, it means that GPT-4 is choosing your model response instead of using the other response. So you can see that the GPU is kind of more stable along the way and gradually decreasing at the end if you increase the sensitivity or the temperature. So this is an example from the paper. The prompt was that a person was about to propose to his girlfriend, he couldn't sleep, he was anxious, and the DPO said exactly what it means in a very short response, but here PPO was kind of straightening it and didn't get the exact points that the prompt was mentioning, and the GPT-4 chose the response given by the GPO. The third one is the dialogue. So the dataset was Anthropic RLHF dataset. Is actually a 170K conversation between human and AI, and the model was Pythia 2.8b. You can see that I have highlighted the word line, no SFT module is available. So the paper, if I can go here, they mention something. If you have a phase 1 supervised fine-tuned model, you initialize that model as your reference. It's pretty clear that we saw. But what if you don't have a phase 1, you don't have a supervised fine-tuned model? What do? You then initialize the reference by only fine-tuning with the preferred responses. They said that it was the best way, it's kind of equivalent. So for that third task, they didn't have a supervised fine-tune, so they did that. They fine-tuned a reference model using only the preferred answers. And the evaluation is still GPT-4 win rate, and this is your GPU line. So I had a question when I was reading the paper. There is a green line that's above the threshold maximum time. So they said that this is actually based on 128. So what does it mean? They said that they collected the best 128 dialogue and they picked one using a reward, and they said that yeah, it works better than the DPO, but it's very computationally heavy. That's their explanation. So this is the example from the paper. The prompt was that I'm trying to find a location or address of a person, and the DPO was like, it's a privacy matter, I'm not going to give you the address. But the response that in the test set was generated is that I know this person, it lives here, he was there, and he gave out the address. And the judgment was that they chose the DPO response. So I'm almost at the end of the presentation. So they mentioned many things as the limitation, but what I understood from the limitation is that they are trying to train their GPU within a distribution that they created. How will the GPU work if you want to train it out of distribution? What if the prompt changes? What if the domain shifts? So they didn't mention. They said that it can be more optimized if you can train it with maybe unseen data, if you want to say it maybe more specifically, unseen data. And also the reward over optimization. So the previous methods or process use an explicit reward model, and the concept of reward optimization can be understandable, but our DPU doesn't have an explicit reward model. How do you acknowledge if there is a reward optimization phase? So it can be maybe reduced because of reduced diversity, maybe exaggerated preferences. So they said that they need to understand this effect on the DPO process as well. And they gave some direction for future work, and it's very simple. They said that we only evaluated models up to 6 billion parameters. Maybe in future you can explore more larger models. And they also said that we use GPT-4 as the evaluator. Maybe more high quality judgment is possible if you like look for other ways. So the conclusion is that direct preference optimization is simplifying the objective. So you can, instead of using an training or explicit reward model or a complex reinforcement learning, you can do it with one loss only. So it's more simplified, but even with a simplified approach, they are doing, as their graphs and statistics saying, much better than the previous models. This is the reference of the paper. Yes, that's all from my side. Thank you.
I have one question. So this